dynamic programming is a technique used in solving complex problems by chunking the big problem into smaller problems. But the key point in dynamic programming is to solve the smaller problem only once. So when we need to solve the smaller problem again, it's only looked up. It's saved in a memory, and we look it up directly. I will show you now a simple example, the Fibonacci numbers. The Fibonacci numbers are defined as follow: f of 0 equals 0, f of 1 equal 1, and f of n equal f of n minus 1 plus f of n minus 2. Okay, how do we compute the nth Fibonacci number? There are several methods to do it. One of them is to use the definition, which is big O of 2 to the n, which is exponential. It's just simply if n equals 0, we return 0. If n equal 1, we return 1. Or else we return Fibonacci of n minus 1 and plus Fibonacci of n minus 2. This is a very slow method. Another solution is to solve the recurrence equation and do some more math, and we can solve it in big O of log n. But in this method we use doubles, not integers, nor long. And we can compute it using the closest integer function, which is with the phi, which is the golden ratio, square root of 5 plus 1 over 2. We power it to the n and divide it then by square root of 5, and then we compute the closest integer function, which we add half and take the floor of it. Now I'm going to talk to you about the DP solution of computing the Fibonacci number. First of all, I'm going to introduce the top-down approach, which starts by solving the big problem and then chunk it into the smaller ones. Notice it's very similar to the exponential solution. It's the first 3 lines. There are 3 lines which are similar. If n equals 0, we return 0. If n equals 1, we return 1. Or else we return the Fibonacci number of n minus 1 plus Fibonacci of n minus 2. With this method, we add an array, a huge empty array, so that we can store the computed results before. If we are computing the nth Fibonacci number, we store it in dp of n, and next time we need it, we check if dp of n is different than 0, and we return it. So let's say if we are computing the 10th Fibonacci of 10, we need to compute the Fibonacci of 9 plus the Fibonacci of 8. And to compute Fibonacci of 9, we are computing again Fibonacci of 8. In this method, we compute Fibonacci of 8 once, not twice, which makes computation faster. I'm going to show you another DP solution which starts bottom up. I'm sure most of you who solved the Fibonacci number have used it before, but didn't know its name, which is the iterative solution, which starts by solving the smaller problems, which is Fibonacci of 0 and Fibonacci of 1, which are the basic, and then we build up to solve the bigger problems which we need. Okay, now I'm going to show you the basic of dynamic programming, which is the basic problem to solve in dynamic programming, which is the knapsack problem. I will use as an example the knapsack problem posted on Sphere Online Judge. Here's the link. Okay, the problem says we have n items, and each item has a size and a value. And we have one knapsack of size S less than 2000. Our task is to fill the knapsack with items that maximizes the value without exceeding the size. We need to fill the knapsack with as much possible items as we can without exceeding the size and by maximizing the value. Well, to think about it, you can think about it as an exponential problem, which we try all the possible sets, which is 2 to the n sets. We start off by doing this, and then add the DP trick. I defined S as the knapsack size, N as the number of items, and then the list of the item size, then the list of the item values. And the DP, which will store the previously solved problems, that links the size that we are currently on to the ith item. And when solving the problem, if I equal to n, which I is the ith item that we are currently adding to the knapsack, and size is the current size that the knapsack is filled with. If the knapsack is we are beginning to with complete knapsack and decreasing it. If the size becomes 0, then the knapsack is full and we return 0. And if the ith item is equal to n, there is no nth item because we start by 0 and the nth doesn't exist. And this line shows that if this problem have been solved before, we return the solution directly. Now, to solve the problem, there are two options: either to take the item or to leave the item, which makes the exponential trick. So, if the item can be added to the knapsack, we take option 1 as taking the item by reducing the size by the current item size and increment the item number by 1 and add the value of this item to the option 1. And option 2 leaves the item without adding the item value and without removing anything from its size and increment one item. And the solution for this current problem is dp of size and I. It's the maximum between option 1 and option 2. I hope it's clear. Here are some useful links that you might want to check out to solve other problems, including dynamic programming and other stuff. Topcoder, Sphere Online Judge, UVA Online Judge, ProjectEuler.net, Google Code Jam, and Facebook Hacker Cup. Okay, thank you very much. Here's my username.